Morning, guys. So we've reached the end of our second chapter here on equilibrium. Pretty much at this point here, we've introduced what is the equilibrium constant expression. Basically, is this product over reactant ratio. We're going to achieve a new equilibrium at a new temperature. Today, what we're going to do is we're going to actually put in some of the numbers, put in some of the math as well, and we're going to see how, given a certain list of unknowns here, we can make use of this equilibrium constant here, make use of which direction things shift towards to actually find some missing concentrations. So this part here, we're going to look at equilibrium concentrations. For us, we're only going to deal with homogeneous equilibria. Homogeneous means everything has to be in the same state. And in this chapter, we're going to mainly deal with gases. This sort of avoids the, solids you have to ignore, pure liquids. If it's the only L in the equation, you have to ignore it here. That sort of avoids that a little bit. So you'll probably recognize it's the same equilibrium systems that we're dealing with. This time, instead of just a mere does it shift left or shift right, we're actually putting numbers to this here. So for starters here, let's study this process here. You should be able to identify from yesterday. This is called the Haber process. Iron is the catalyst that we need. The catalyst itself is heterogeneous, but at least the equation itself just deals with gases. So for starters here, we'll begin fairly easy. We have a 5-liter flask, so I have a 5-liter container, 5 liters worth of room, and what I decide to do is I have 1 mole of N2, I have 2.5 moles of H2, and I have 12 moles of NH3. Right, so I went in with a meter here, and I actually figured out how much N2, how much H2, how much NH3 that I have. Let's start off, and this question here is just calculating Kc. So Kc or KEQ here, we know in general it's supposed to be products over reactants. Because the equilibrium constant is going to need concentrations, that's the first thing that I'm going to do. Even though they give me these things here in moles, I'm going to figure out what the concentrations are. And one important note in this question here is we are currently at equilibrium. These are the values when we've already hit equilibrium when forward rate equals reverse rate. It was not proceeding towards equilibrium. So let's just do this here. What's the concentration of N2? If you just remember, concentration is just moles over volume. So I have 1 mole divided by 5 liters worth of room. So that gives me 0.20 molar. In a similar fashion for the hydrogen, I'm just going to put subscript EQ for equilibrium. Hydrogen is actually 2.5 moles divided by 5 liters. This gives you 0.50 molar. And then the NH3, well, we have way more NH3 here. I'm sort of thinking that products are favored here, but let's just verify this. I have 12 moles at equilibrium. And this one here is 2.4 molar. Right. Keep track of your sig figs and all that. All right. So right from the start, just looking at the numbers, I know I am at equilibrium. I know that there's not going to be any overall change. At equilibrium, I'm going to have some N2, I'm going to have some H2. Those are all present. But just looking at these numbers here, I have way more NH3. I am at equilibrium, right? But I'm at a certain temperature where products are heavily favored. At equilibrium, macroscopically, it looks like nothing's changing. But what's ending up happening is the N2 is finding 3 H neighbors. I didn't draw enough H's. 3 H neighbors here. That's constantly becoming NH3, as one of these NH3 is going to constantly fall apart to become N2 and 3 H2s as well. So if I could tag any one of these chemicals, it's like the line changes are still occurring, but overall it looks macroscopically nothing's changed. In this case here, because ammonia is a product, I would imagine that with more products, I would imagine the Kc is large. So let's just try it out here. For starters, I would write out the Kc expression. Even if I know the numbers ready, I just want to make sure I don't accidentally drop any powers. The coefficients go up into the powers, NH3 squared. I have N2, I have H2, all of them are gases, all of them are included. And since I already have all the values at equilibrium, it's just plugging and play. So here, the NH3 is 2.4. I'm going to take that squared, divide it by 0.20, which is the nitrogen, the hydrogen, which is 0.50. Sure, I need to do a little bit of work to get to concentration, but aside from that, getting this number here is not all that hard. 2.4 squared divided by 0.2 divided by 0.5 cubed gives me here, my Kc is 230. They did not tell me what temperature I'm at, but the ratio is 230. And in this case, as we had expected here, because the Kc is so much larger than 1, we know products are favored. Even though we are at equilibrium, even though constantly reactants become products and products become reactants, we are at a temperature where we have way more products that can be seen based on these numbers. I have 2.4 of this, and I only have 0.2 and 0.5 of the other one. All right? Let's compare just the general overview here. compare example 1 with example 2. What's different about them? In example 2 here, let's read, well, same equation. All right, so this time we have 5 moles of NH3. Okay, the bulb is twice as big, fine. So this is now a 10-liter container. I divide by 10, ooh, big difference. Notice here, I put in 5 moles of NH3, right? Did I actually put in any N2 or any H2? Wait a second. In this case here, we've only started with products. So currently, I would refer to this initially. This is going to be, we're going to start up an ice table here. The initial amounts are 5 moles of NH3. I actually didn't toss in any N2 or hydrogen. So if I just did that calculation on the side here, I can say, what is the ammonia that I added, I, for initial? I added 5 moles worth of particles. The container is 10 liters. I've added enough for 0.5 molar. Because there is a sense of time passing, I'm going to need to wait until the system has reached equilibrium. I'm going to need to set up what's called the ice table. I prefer it like ICE. Mr. Barry does S for shift, doesn't really matter. C would just stand for change. So fundamentally, what's different about example 2 and example 1? Example 1, we had a container. We were given the amounts, but that had already reached equilibrium. In this case here, the 5 mole that I pumped in, that's just initial. We calculated the concentration is 0.50. Usually for this, what's referred to as ice table, use concentrations for your ice table. And your ice table is basically just a mapping of what information do I know. Is this a starting value or is this an equilibrium value? So I pumped in enough NH3. I have absolutely no N2 or hydrogen around, but I have the concentration initially under the NH3 as 0.50. Notice I don't need to say, oh, by the way, I didn't add any N2 or hydrogen. I just didn't tell you I added those in. So it's understood that those two start off at 0. I start off with a situation that we are all products to begin with, so be it. That's fine. We saw from earlier, I can reach equilibrium from either the reactant side or the product side. And then what they do is they come in and they say, oh, by the way, at equilibrium, the concentration of hydrogen is actually 0.16. Where did that 0.16 come from? Initially, I didn't put it in. Oh, that's right. The products actually would start forming reactants. By the time you hit equilibrium, this number here is 0.16. Right? So initially, you did not add in any N2 or hydrogen. But there we go. We got this equilibrium. Now what we want to do here is we want to do the change. So over the course of the reaction, as the ammonia sort of got consumed, we end up generating nitrogen and hydrogen. What I want to note for this change line, the change line follows the mole ratio. Because the change line is based on the recipe, based on the balance equation, for every 2 ammonia that I lose, I'm only going to get 1 part N2 and I'm going to get 3 parts H2. If I know that the hydrogen increase, so I have a plus, 0.16, well, nitrogen is also on the same side, so this is going to be a plus. I know the other side here has to be a minus. I had to lose products for me to overall gain reactants. But based on my mole ratio, as I gain 0.16 of hydrogen, I only gain a third of that 0.16. 0.16 divided by 3, not a super nice number, but 0.053. So as I picked up 3 parts hydrogen, I only pick up 1 part nitrogen. Anytime you have the I and the C row, I would just do the math. So what's 0 plus 0.16? 0.16. 0 plus 0.053? 0.053. Right? Those are positive. Right? How about the other case? Well, the reactants had to have formed from something. They were formed from consuming the NH3. So let's take this 0.053. This is the 1 part ratio. If I times that by 2, it gives me that this one here has to change by 0.11. We know it has to be a minus because in this case here, products are consumed versus reactants are picked up. Give or take a little bit of rounding here, we have 0.39. So all the numbers on this case here are all concentrations here. It was a little bit of work because they only gave me a starting number for NH3. I wasn't at equilibrium. They gave me one ending number, so I can figure out what the change is. By ratio, I can figure out all the other numbers. In general, if you know all 3 of these numbers, you're ready to plug them directly into case C. Even though I have the numbers like earlier, I would still write out the expression so that I don't accidentally drop a power. And now this is exactly like example 1. What if I said, oh, by the way, I'm in equilibrium where 0.053 is nitrogen, 0.16 is hydrogen, 0.39. We can just work out this ratio here. So 0.39 squared divided by 0.053 times it by 0.16. Don't forget to do those powers, the cubes and the squares, from the balance equation there. 0.39 squared divided by 0.053 divided by 0.16 cubed. I'm getting roughly 701, so 700. 7.0 times 10 to the 2. Again, Kc is bigger than 1. This implies that the products are favored, even though not by as obvious this time, but you see we have more products than reactants. Sometimes because of the powers here, it doesn't perfectly work out, but as a general rule, the bigger the K, it means products are favored. So products. So more products at equilibrium. So yes, we've hit a balance. Yes, we've hit forward rate equals reverse rate, but we actually end up with more products at equilibrium. All right? So let's see a couple different little shifts of this problem here. In this question here, some NH3 was introduced to a 2-liter flask. If you can, I would just start off with a picture here. So I start off, I add a question mark amount of NH3. At equilibrium, there were 0.80 moles of N2 present. So that's the initial. At equilibrium, at the end of the day, we actually have 0.80 moles of N2. So like before, where did the N2 come from? Well, it was as I hit equilibrium. They tell you here the Kc value, so we have some unknowns of the other chemicals, but they actually give you the constant here. The question this time is, how many moles of NH3 did I pump in initially? Right? So because there is a sense of time passing, there is a introduced, and there is a later on at equilibrium, I'm going to set up my ice table. Currently, I'm going to put in an unknown amount of NH3. I could put the X, but I'm just going to call it Y, just for my unknown here. So I put in some unknown amount of NH3. My goal is to figure out the moles of NH3 in this case. Again, what's implied here is I've added an NH3. I didn't say I added an N2 or hydrogen. And in that case there, I can say, well, no N2, no hydrogen. We need to decide in the change line which side is plus, which side is minus. Well, 0 is as low as you can go. I can't get negative concentrations. So in this case here, I know these two sides here have to be plus. I have to gain reactants by forcing some of my products to form the N2 and hydrogen. I'm going to lose my products. Later on, we're going to see a question where if I don't know any of these changes, I'm going to use an X and I'm going to follow the mole ratio. Phew, this time they actually tell you at equilibrium, we actually know how much N2 I have. Let me just do that on the side here. What is the N2 at equilibrium? I just want a concentration. So 0.080 moles of this chemical. I'm a 2-liter container. So 0.40 at equilibrium. So at the end of the day, the N2 is actually 0.40. If you know, well, I started with none, and now at the end I have 0.4. I know I had to have gained by 0.4 there. This one here has to follow the mole ratio. The change line is the only line that follows the mole ratio, right? So therefore, if I gain 0.4, that's 1 part. I'm going to gain 3 times as much hydrogen, plus 1.2. I'm going to lose 2 parts of NH3. I'm going to lose 0.8. Anytime you have the I and the C or the S row here, you just do the math. 0 plus 1.2, well, 1.2. Y minus 0.8, Y minus 0.8 there, right? Again, I'm just emphasizing here, it's only the change line that follows the mole ratio. It's always very tempting to be like, oh, if this one here is 0.4, then the other one has to suddenly be 0.8 or whatever. The exact amounts actually don't matter. It's only when we actually do the reaction that we actually follow the mole ratio. Okay, more on that in a second. So we have Y. Y is the amount initially put in. Right, that's my starting NH3. I started with all products. Anytime you have this equilibrium row, you're ready to actually do the Kc expression. So let's just punch through the Kc expression here. Kc is ammonia squared divided by N2 divided by hydrogen cubed, like that. So I have my Kc value. It's this 7.0 times 10 to the negative 3. My ammonia, I'm just going to put in, I have no clue what it is, but I'm going to put it in as a placeholder. You plug in the equilibrium row because the equilibrium constant needs the equilibrium concentrations. These have to be the values once I've hit that balance. So I'm going to have on top Y minus 0.8 squared divided by the N2, which is 0.40, divided by the H2, which is 1.2. Don't forget about the cube. In this case here, let's just clean this up a little bit. I'm going to bring the denominator up. So 7e negative 3 times 0.4 times 1.2 cubed. That gives me 4.84 times 10 to the negative 3, give or take. Y minus 0.8 squared. This one here could mathematically end up as a quadratic, but just a simplification, we don't need to use quadratic formula. So in this case here, they've given you the right amount of variables that we can just take a square root. So if I just square root both sides here, keep the whole answer in your calculator if you can. The root of this 4.84 number here, so take the root. That's going to give me here 0.0696 is equal to y minus 0.8. and therefore the y, when I add that 0.8 over, the y is equal to 0.87. Right? Now, it could totally be a lot of work for you to do this algebra here. Do yourself a favor and always reread the question. What were they after? In this case here, they were interested in how many moles of NH3 did I put in initially. I look across the initial row, I look down the NH3. Oh, great. Y is actually the number that I want. This is close. But remember, on the ice table, unfortunately, these ones here are all concentrations. How would I find the moles of NH3 if I know the concentration? Well, the container remains as a 2-liter size. So let's take 2 liters. Let's multiply this 0.87 molar. And let's give it here 0.87, take the whole number through, times 2. This now says I put in 1.7 moles NH3 to begin with. I didn't have to put in N2 and H2. I didn't need to follow the mole ratio. But over the course of time, I would have lost a little bit of this, regenerate N2 and hydrogen, so that by the end of it, the Kc is the 0.007, like it wants to be. This Kc here happens to be very tiny, so this Kc is a lot less than 1. So in this case here, I would say reactants are favored. So I actually have the 0.4 and the 1.2 here. If I take a y, the y was 0.87. 0.87 minus 0.8 is basically 0.07, so way little product, so that's consistent. Right? How come the Kc's can be different in these 3 examples? Aren't we looking at exactly the same expression? What is the only factor that can change Kc? Remember, we did the derivation. Kc, somewhere behind the scenes, it's this ratio of the rate constants divided by each other. The only way that this could happen, they didn't specify, but in this case here, we can say Kc's are different for different temperatures. They didn't specify what temperature I'm at, but because I can see that the values are different. At first, the Kc was we had a Kc of 230, and then it was 700, and then it was this 0.007. How could it be different? It's because we're at different temperature. Right? So that's the basic ideas here. We're going to study through another shift or two in the problems, but just carry around those ideas here. This next part here shouldn't be that difficult as we walk our way through. So let's try it out. Example number 4. So a new equilibrium. Consider this equilibrium. We have a container. This one here is a 1-liter flask. We pump in 2 moles of the CO. We're going to pump in 3 moles of the H2O. As well, I'm going to pump in 1 mole of CO2. And I'm going to pump in 1 mole of H2. Okay. So this one here, is there a sense of time passing? This one here, that's what it contains at equilibrium, right? So those are the amounts. This is already at equilibrium, so we can find our Kc from there. And then what I decide to do is I mess everything out. I poke at the system. I then add some extra CO. By adding that extra CO, I upset the equilibrium. That would be my new, sort of my initial line here. What's the new hydrogen after equilibrium is finally reestablished again? So there's sort of a couple things happening here. I would actually start off with an initial. You can even have a sort of shift row right in between here, just to keep things a little bit separate here. And you'll see why in a second here. So they gave me a bunch of these values here nicely because the volume here is just 1 liter. If I divide by 1, it's just going to be concentration, right? So in this case here, I pumped in 2 moles of CO. So under CO, initially, we have 2 moles divided by 1 liter, so this is 2 molar CO. The H2O, I pumped in 3 moles divided by 1, so I have 3 molar H2O. The CO2 was 1 molar, and the H2 was 1 molar. You really don't need to put concentration, like the unit, in there, because I know going into this, it should be a concentration. Currently, this is already at equilibrium. They told you that. So this is actually our starting equilibrium, our initial equilibrium. Because we are at equilibrium, I can actually find what my Kc value is. So my Kc is products over reactants, CO2 times H2 divided by CO times H2O, right? Anytime you have what's equivalent to the E row, you just punch it straight in. So the CO2 here was 1, the hydrogen was 1, divided by CO, which is 2. The water here is 3, so I go 1 divided by 6, gives me my constant is actually 0.167. So as long as I'm at this temperature, My Kc is 0.167. Again, you can interpret this for yourself. This means reactants are favored. We have more reactants, even though by the time we've actually hit equilibrium. And now what I do is I now come in and I poke at the system. I stress it out. I do a little bit of Le Chatelier. So what I do is I decide we were happy at equilibrium. My stress is I then pump in an extra 1 mole of CO. Right? It's still in a 1 liter container. I then add basically 1 molar CO. So my shift, my poking at it was CO. I then increased it by 1.0. Right? I didn't stress out the other ones, so nothing changed for the rest. Now we're totally out of equilibrium. Now we're not at our 0.167 ratio anymore. What has to happen here is we need to shift. Well, let's do our Le Chatelier. If I come along and my stress is I increase CO, which way do we shift towards? Well, you should be able to say to me, we shift away from any additions. We want to shift towards products. That guarantees the reactants are going to drop. This side is going to be minus. The other side has to be plus. Uh-oh. Unfortunately, they did not give you any of the equilibrium rows. On the back side, they did give you at least one of the numbers, so then you can work out from the change line the other ones. If you're not given any information for the last row here, you're going to use x. Because these are all in a 1 to 1 to 1 ratio, I can just say minus x plus x plus x, right? Still looks very confusing, but my ice table is trying to lay out these numbers for myself. And now, like I mentioned before, whenever you have these top two rows here, you just do the math. What's 1 plus x? Well, 1 plus x. 1 plus x. 1 plus x. 3 minus x. 3 minus x. 2 plus the one I added is 3 minus x here, so 3 minus x here. Right? So because it was an unknown here, it was an x, but I just got to remind you here, it's only the changed line that follows the mole ratio. That's the only time that the reaction actually is occurring. Just because it was a 1 to 1 to 1 ratio doesn't mean, oh, I put in 1 molar CO2, 1 molar H2, I have to go 1 molar CO or 1 molar H2. It's totally up to me how much I put in. It's just when the reaction occurs, and the only time, as I'm trying to emphasize here, the only time the reaction is occurring is during this change line. So even by the end of it, it's most likely not going to be a 1 to 1 to 1 ratio, but that was because of how much I put in initially. Anytime you have this equilibrium row, as I mentioned before, you're ready to punch it into the Kc expression. I'm just going to rehash the Kc expression for you here again. Products over reactants as it was written for you. CO and H2O like this. Because I already calculated my Kc earlier, this number is what it should be at this temperature. All I did is I shifted the equilibrium by changing concentration. My Kc is unchanged. This is what it should be when I'm back at equilibrium. So I needed the equilibrium values at first to find Kc, and once I know what Kc is, then I'm ready to do math for the others. So I'm going to punch in the 0.167. You can make a note to yourself. This is because we were at the same temperature. The numbers may be all wacky now, but because I didn't change temperature, my rate constant didn't change, my equilibrium constant also doesn't change. Because you have these two values here, we have a 1 plus x, all over a 3 minus x, and 3 minus x here. I can summarize that a little bit here. They kept the numbers fairly simple for you, so we just have those things being squared. It could mathematically end up as a quadratic, but again, I mentioned we don't need to use quadratic, and the reason why is I can just square root to get rid of this. So let's just take the root of both sides. What's the root of this 0.16 repeated number here? The root of it is roughly 0.408. The square root will kill both of the squares, if you remember your exponent rules here. If you do square root of a squared and b squared, the square root will kill both of the squares and just leave you with a and b. So now, a lot easier here. We have a simple 1 plus x and a 3 minus x. Just going to do the rest of the math over here. I'm going to bring the 3 minus x up. So 0.408 times it by 3 minus x. This is equal to 1 plus x. I'm going to distribute the 0.408 in. So 0.408 times 3 gives me roughly 1.22 minus 0.408x has to be 1 plus x. I'm going to collect like terms, so 1.408x has to equal to 0.22, and the x is therefore 0.22 divided by 1.408, give or take a little bit of rounding here. I'm getting an x value of about 0.16. Right? Now, that was a lot of work, a lot of algebra to actually get us to this number here. We needed to set up ice table. We needed to find the Kc first and then do this here. Still, do yourself a favor and reread the question. What were they actually looking for? They are interested in you telling me, what is the hydrogen as the equilibrium is reestablished? So let's look down the hydrogen row. Hydrogen is right here. Let's look at the new equilibrium row here. They actually want the answer as 1 plus x, not just x here. So we can actually conclude the hydrogen at the new equilibrium is 1 plus this number I did so hard to find, and I get 1.16 molar or 1.2 molar, and there we have it. That's done. Okay. So let's just try it out here. Next example. One last twist to our setup here. So let's just read through the question here. At a temperature of 75 degrees, at this first temperature, we have Kc is 133. So that just means products are favored, right? For the equilibrium below, so same equation as we did here. If 5 moles of CO2 and H2O and CO are added to 1 liter flask at 75 degrees, which direction will it shift? So let's just draw a picture. Let's deal with that part of the problem first. We have a container here where, again, a 1 liter flask dividing by 1 doesn't really change the number. So I know I have my initial row here. I start off with CO2, which is 5 moles, divided by 1 liter. 5 divided by 1 gives you 5 molar. So 5 molar of the CO2, 5 molar of the H2. That's what I pump in initially. So I pump in CO2, I pump in H2. Just because it's a 1-to-1 ratio doesn't force me to have to pump in the same amount of H2O and CO. Case in point here, I just pumped in 1 molar of water, 1 molar of CO. This time here, what's tricky is we actually don't know the direction that we shift. We don't know which side is plus or minus. Previously, it was obvious because if one of the sides were 0, that side has to be plus. I can't drop any lower. In this case here, because I have a mixture, right, starting some mixture of reactants and products, there's a good chance that I'm not at equilibrium yet. The first part of the question is, which way do I need to shift to reach equilibrium? You can think just sort of intuitively here. You can say, well, the KQ, KC is actually bigger than 1. Products are favored. That already is products are favored. But the question here is, given these numbers as I have it, do I have enough products that the ratio is actually large enough for what it needs to be? So let's just make this note here. If unsure which side is plus or minus, we don't know which direction we're wanting to shift it to, what I want you to do is I want you to check your Q value. And remember Q we had introduced a couple lessons ago here. Q is basically a test KEQ. It's basically what is the ratio currently. So if I try to do this test ratio here, I would do CO2 times the hydrogen times the CO times the water. Normally you would wait until you get this equilibrium row before you actually punch things in. The test value here, I'm just trying it out. I'm going to test it out with all the initial values. Test KEQ using all the initial or the current concentrations. It'd be a total fluke if the random amounts that I put in, it already is at equilibrium. So let's just try it out here. What is my fraction currently? So in this case here, I'm taking 5 times it by 5. So that gives you 25. I divide it by 1. I divide another 1 here. My test value is currently 25. Well, what's the KC supposed to be? When I'm at equilibrium, this ratio is supposed to be 133. I'm only at 25 right now. So in this case, my Q is too small for my KC. Now KC is not going to change. My KC is just going to stay fixed. This number here is 133. You need to climb to 133 before we're at equilibrium. So what I need to do is I need to take this test value here. This test value here is a product over reactant ratio here. I need my value, currently is 25. I need this value to increase. For this value to increase, I need the fraction to go bigger. For the fraction to go bigger, you need more products, less reactants. So therefore, if I said less reactants, now I know which side is minus. I need to have more products. So back to my analysis from before, no, currently as products, yeah, you have 5 of each of them, but still not high enough to actually hit the number that you actually need. So in this case here, we're actually, what direction does it shift towards? We actually shift right to reach equilibrium. Now be careful, I'm not poking at it, I'm not stressing out the equilibrium anyway. It's just that at the beginning, I was not at equilibrium, my value, my ratio was only 25. I need to have it big enough to be 133. I need it to get bigger before it actually hits KC. In this case here, likewise, we're not given any information for equilibrium, so let's just call it X. Nicely, the change line follows a mole ratio, so X for all these ones here. When you have the first 2 lines, you just do the math. 1 minus X, 1 minus X, 5 plus X, 5 plus X. So I predicted which way it shifts towards here. Now we're ready pretty much to do the math from earlier. Let's write out at equilibrium, if I had these expressions, at equilibrium, it should be 5 plus x times 5 plus x divided by 1 minus x, 1 minus x. And my Kc, they already told me, by the time you're at equilibrium, this one here should be 133. I'm ready to put in that 133 here. That is that Kc expression. Remember, these ones here are squared, so let me just take square root of both sides. Root of 133, very similar to the question that we just did, is going to be 5 plus x divided by 1 minus x like this. Bring the 1 minus x up. And I'm just going to solve it over here. I'm going to distribute the 11.5 in. So this gives me 11.5 minus 11.5x has to equal to 5 plus x. I'm going to collect up the like terms. So I'm going to add everything over, let's say, to the right-hand side here. 12.5x is equal to 11.5 minus 5, so give or take 6.5 or so. And the x that I get here, 6.5 divided by 12.5, gives me 0.52. Right? So that is my numbers here. Again, just reread the question. Did they actually want x? Uh-oh. In this case here, determine the equilibrium concentration of each species. Whew, we actually need to do this here. But again, that's just x. The equilibrium concentrations are still either 1 minus x or 5 plus x here. When we reread the question, we actually now can say, well, the concentration of CO at equilibrium is equal to the concentration of water at equilibrium. We had to place the 1 minus x for there. 1 minus 0.52 here. 1 minus this answer says the concentrations are 0.48 for those two chemicals. For the CO2 and the water, the CO2 at equilibrium is going to be matched up with the water at equilibrium. That's actually going to be a 5 plus x. The x here we found, what x solves it out is 0.52, so therefore 5.5 molar is our answer. Right? So even though it may be a lot of algebra for you to actually solve for this x here, you should be able to sort of backtrack and reread the question telling me what they're actually after. There is actually one other important question here, sort of a part C to this question here. I want you to tell me, given that the Kc is actually 350 at 200 degrees, can you predict whether this reaction is endo or exothermic, right? Problem here is they didn't give me the heat term, they didn't give me a delta H term. I don't know whether we're ex or endo. Well, I know, let me just list it for you. I know at 75 degrees, my Kc was 133. I know when I increase that temperature to 200 degrees, I notice that my Kc actually becomes 350. So from those numbers so far, I can say, which is it? When I increase temperature, the Kc actually gets larger, right? We saw a couple lessons ago here, now we come sort of full circle. It was either only for endothermic or exothermic. If it completely confuses you, just guess, okay? So let's guess. Maybe it's endo. Would this work? Well, let's try. Kc is going to be sort of B over A like that, okay? If I increase temperature, yes, the entire system, the whole box heats up. As I heat up the system here, equilibrium doesn't like that stress. It shifts away. I'm going to shift away. I'm going to produce more B and less A. More B and less A would overall increase the fraction. Oh, perfect. If I increase the temperature, it's for an endothermic reaction that ends up doing this. What if I had guessed the opposite? What if I had guessed C becomes D? We're at equilibrium. This is plus energy or plus heat term. What if I increase temperature there? In that case there, if I increase the temperature, I'm focusing just on the heat term. I shift away from there. Therefore, my D actually drops and my C actually increases. When I do my ratio then, this ratio here is actually going to be a lower number. So that's why you don't need to memorize it here. You can just predict it. In this case here, because I increase temperature and it shifts right, we can predict, nope, the endothermic one was correct. I'm going to leave you with these last few couple problems here. I already did this for you in an earlier lesson. So what if I reverse the reaction? What if I go from A to B? What if I make it B to A? See if you can figure out what's your effect on Kc. In general, it should only be temperature changes, but here I'm sort of cheating. I'm actually changing the equation itself, and I'm just saying what's the relationship. They give you a numerical example on the backside here. So in this case, I have my equation. They gave me the Kc is currently 0.04. I know that number there should be true for this temperature. As long as you don't change temperature, that number doesn't change. But now they say, can you compare that reaction to this other one? And if you compare it to the other one, what I've done is I've actually reversed it. Think about what happens to the Kc when you switch reactants and products. And you've also halved everything. And again, we track down what happens to Kc in that situation. You can actually relate Kc, the new Kc prime here, should be the reciprocal of the half reaction, right? So give that a try, verify that for yourself here. Do some practice with these ice table problems. If there is no sense of time passing, you already have the equilibrium numbers, you're all set. If there is a sense of time passing, you need the ICE. It's only the change line that follows the mole ratio, and you match it up against the numbers that we have there. Okay? If you have any questions, just let me know. Thanks, guys.